So looking here, we have that variable of b, and when we look at the array for it, we have values that are similar to this, similar to these initial guesses that we have. So if you look at these, we can see these look similar, but then when we look at this first value, we can see that doesn't look anything like that coefficient before that, that Reynolds number of that 0.023. So if we want to look at the value that would be similar to that, we need to do the exponent of this first element, because you can see in this in the code above that we took the natural log of that value, so it's not representing that similar value. So what we can just do is print, and then we're going to take the exponent. We're going to take the exponent of that that first element in that array. Which the indexing starts at 0. And we can see that we get a value that is closer to that initial guess. And it's not exact because we did that experimental error before. So now what we want to do is we want to try to minimize the difference between the model and the experimental data. So let's do that. So first we want to define a function. I'm just going to call it sum sq for sum square. And this p, it represents the parameters that we are going to define. So those initial guesses. So what we want to do is we want to minimize this function and then return minimal values. So let's see. We want to return the sum of that Sherwood number subtracted from that first element that we're going to provide. This is that Schmidt number, and we can see how the format of this is going to look like this. So this just allows us to find those deviations, and so we want to make those deviations as small as possible. But those deviations could be positive or negative, so they could eventually cancel each other out. So what we want to do is we are going to square this difference so that we return all positive values. We're going to square that, and oops, then I want to minimize. Use the minimize function that we stated above. We're going to import the minimize function from SciPy. So that's sum square. And then, so we're going to give those initial guesses. So that would be that 0.023. That 0.83, and that 0.44. Okay, so what I want to do is I want to add a comma here. So I can define that function and those elements in the array, those initial guesses. And then we can see that we return values. And they are also somewhat close to those initial guesses, but these should be the returned minimized values. All right, so now we want to make a figure. So let's do that. So we're gonna give a variable for that figure, and it's going to make a subplot. And then, so I want to start from a blank slate, a blank plot. So I can add to that plot by adding traces. And now to add those graph objects of the scatter plots, we can just use that geo, that abbreviation I use for graph objects, and we want it to be a 3D scatter plot. So then I'm going to put scatter, and then 3D. And so the x variable for that x-axis is going to be that Reynolds number. The y is going to be that Schmidt. And that z is going to be the Sherwood number. Now for mode, I'm going to say that I want them to be markers, and the other choice could be maybe lines, which we will use later. But right now we are just going to use markers, which are those individual points of that you can see on a scatter plot. So those individual data points is what I'm trying to say. And then I can also change the color of those markers. So let's say I want to make them blue, just to add some coloration. Oh, I can also change the size of those markers so that we can see those individual points clearly. So that should be good. So shift enter that. I think that's plural. Oops. Okay. I don't know if that looks right. Let's see. Oops. So here's my figure. Can I change this? Ah, okay, that looks a lot better. Okay, that looks fine. So let's do something about this. Oh, so you can see that the dependent variables are going to be the Schmidt and the Reynolds number. The Reynolds number. Oh, that's no wonder that looks weird. That's supposed to be the Schmidt number. Okay, that makes a lot more sense. Let's see that. That looks a lot better. I thought that looked weird. Ah, okay. That makes a lot more sense. So you can see that the dependent variables are the Reynolds and the Schmidt number, with the Reynolds on the x-axis and the Schmidt on the y-axis. So now what we want to do is we want to create a mesh grid to kind of show kind of like a line of best fit, but in this case it's a three-dimensional plot, so we want it to be a sort of like a surface and show the as a mesh grid. So what I'm going to start with is, so now we want to start with something called lens space. And so what I'm going to do first is look at the Reynolds value. So the minimum value could be 2,000. The maximum could be 35,000. And I want there to be 30 intervals, let's say. And then I want to do the same thing for the Schmidt number. And so the minimum is going to be 0.6, the maximum is 2.5, and then I want the same of 30 intervals. So now let's create variables for this. So Reynolds number first, because that's what we put in first. And then what we're going to use is something called mesh grid, and what that mesh grid is going to do is create those pairings between those x and y's values, or those Reynolds and Schmidt numbers. So and then if we look at those values, we can see that the y values are held constant and the x values will vary. And so now we want to look at the Sherwood numbers for this grid. And we want to calculate them given the problem statement and the linear regression we did earlier to find our parameter values. And so we're going to be using those experimental coefficients we found earlier, that B array. And so we can calculate the Sherwood number for the Reynolds number varying along the fixed line for the, actually in this case the Schmidt number will be fixed. Here, we can look at it, so wait, the x, y, holding the y constant, so the Schmidt value will actually be held constant, and then the Reynolds value will vary. So let's just do this first, and we can do that. Exponent. So we're using those values, the elemental values from the array of B. And we're using the grid value, so the indexing starts from 0, so that's why we pulled out that first element using that 0. And then this one's going to have that second element, that third element, be that third element from the B variable, from that B matrix. So now that we have this, we want to use something that is called zip, so that will just pair or combine all three of those variables, so the Reynolds, Schmidt, and the Sherwood numbers, so that we can calculate the Sherwood number for the varying Reynolds along that fixed Schmidt values. So let's just say for I, J, and K. So now looking at that figure, we can add traces for those lines for that mesh grid. So these are only going to be in one direction. So I'm going to use that graph objects function that I defined earlier and abbreviate it. Well, use the abbreviation. And we also want this to be for this 3D scatter plot. And so what's going to happen is we want the x to equal the I, so that these will correlate with the axes, and those x values will be represent the I, or be parallel with the I. Y equal J. Okay. So in this case, we want the mode to be in a line form because it's going to be a grid. And then I want the line color to be white, let's say. Okay. Alright, so what we have here is we have those first series of lines for that mesh grid going in one direction. So let's see what that looks like on the figure with our data. So we can look at the figure. Oops. Okay, so let's scroll up and see it. And looking at it, we can see, yes, we can see those lines going in one direction, but it's in white, so it's really hard to see. So I'm going to change that color. So I'm going to change that to black, so it's easier to see. And then let's look at it again, and hopefully that will help. So yes, that really did help. So now we can see that very clearly. And so looking at this, we can see, so for that y-axis, let's put it around. For that y-axis, we are holding those Schmidt numbers constant for one line, and then varying the x values along that constant Schmidt number, and then so on and so forth for each Schmidt number. And now what we want to do is we want to do the opposite of that. We want to flip those. So we want to then hold the x constant for a line, so that we can vary the Schmidt numbers, so that we can create that mesh grid look. So we can do that fairly easily. So what we just do is we can copy this and just paste it down here. And now what I'm going to do is I'm going to flip these, put the Schmidt number first, and then put my grid, my Reynolds number. And then I need to swap these values then too, so. And that looks pretty good, so hopefully we'll get some of those lines in the other direction now. So yeah, there we go. We got that mesh grid for that model fit for the data. So now we can see that those x values were, those Reynolds values were held constant and the Schmidt number varied. But let's update the figure so we have some labels for the axes. And we can do that by just doing figure.update, and we want to update the layout. That's not right. And let's say we want to change the width and the height as well. Just make it bigger. And then we also want to get rid of these the legend over here, because we really don't need to see all those traces, and they definitely don't need to be numbered. So we want to put that showing the legend as false. And then we want to give those axes labels. So what we do is go to scene, and then dictionaries, because we're I guess defining those axes. And so the x-axis, and then it's for the title of it. And we want to give it the name of that Reynolds number. Then for the y-axis, we want to do the same thing. And last but not least, we have that z-axis. Which is that Sherwood number. Alright, so there we go. We have that updated, let's move this up. We have that updated model. We updated the figure, so now we can see those axis titles, and it does look bigger than before. So it's easier to see. But that's it, so thanks for watching.